Thank you very much for inviting me to give a lecture here. And then it's quite happy to have a very good time in Korea. And actually, this is my second time in class. The last time is 50 years ago when I was a secondary school student. And then, investors quite nervous because I'm the first. This is my first time to give the closing lecture. So that means I had to handle the time. Okay, so now today I would like to talk about the 10 modules of the special linear group, the geometry. Yep. In fact, in the first talk, Professor Choice talked about the representation. The spaces is over the elliptic spaces, and in this talk we talk about over the complex field. So that means here, if you talk about any representation of G, the V here is over Z. Yep. In fact, there's some relation between them. In fact, this topic is also related to the local Linus correspondence. And Professor Choice is talking about is something like the periodic version Linus program. Okay, but here we talk about the local one. So in fact, the automorphic representation consists of the different kinds of we will choose the fixed place of the field K. So in this talk, we talk about only the local case. And now we talk about some setting. We call some object here. The G is a kinetic reductive algebraic group over F. And F here is we shows the local field with the characteristic 0. Now we will denote the GF to be the F rational point sub G. Okay, but as a title, we will talk about the G to be the special linear group, and we will fix our field to be QP or is finite extension. That means F can be is finite. Okay. Now, so some people maybe will have a confusion. What's the 10 module here? In fact, when we study the group G, we would like to know the dual spaces. What's the deal here? In fact, the G, we will call the such kinds of stuff is the equivalent classes of the irreducible representations of G. And then we would like to study the structure of this object here. In fact, now we fix today we talk about is the periodic field and its finite extension. The word of the G hat is quite weird because the construction of the representation of G is totally different from the case happen in the real field or complex field. In complex field or the real field, we will notice everything. Now we choose the G, the same setting, but this is over the complex field or the real algebraic groups. The representation should be constructed from we call the discrete series and the principal series and some this kinds of stuff. And this theory established by the Harry Chandler, just like you mentioned before. By using the harmonic analysis. That's the building block. But in fact, in the case of the p-adic groups, we have the similar story, but it's quite different. We don't have the discrete series will be replaced by so-called the cuspidal representation. Just cuspidal representation, and some induced representation by some silver cuspidal. This is the way to construct the deal here. I will explain it in detail. Okay, so now I will talk about some structure for this. In fact, for any G here, now we choose to be the SLNF. We have the parabolic subgroup. And B to be choose the Borel subgroup. In fact, the G over P is a projective variety. So maybe you don't have some picture inside, or can draw it in the form of the matrix. For example, if we choose the G to be the GL4, okay, the parabolic subgroup is isomorphic to the something like that. Maybe something like that. I choose not N, just N here. It will be more convenient. And then justify to be N. Okay, so that means this is a box matrix. This is what we call the parabolic subgroup. And the Borel subgroup is much same to B, so be something in this case. We choose, this is an upper triangular matrix, and this is 0. So this and form the Borel subgroups. So we have these two cases. So for given any proper parabolic subgroups, we will have a so-called the Levy decomposition. That means we have what we call the Levy decomposition. We have such kinds of semi-direct product. And then here, the M, the U here is a unipotent radical. And M is called the Levy subgroup. In fact, before we talk about how to construct the representation of G, in fact, in our story, everything should be constructed from M here. Now here, we also define the wild group. This is the same thing. I mean, like we can use the root system to define such kind of group. In fact, we have another realization. In this case, this is a quotient group by the normalizer, the M in G, and then modular this one, like this. So for example, if we choose the Levy subgroup to be the torus, so the wild subgroups with respect to T should be the permutation group, Sn. Okay, now I would like to define some basic notion. Now, this is the main object to study is smooth representation. In fact, given any representation of G, we call a vector, and the vector, maybe a vector in V is called smooth. That means there exists an open subgroup K, sub G, open in G, then such that for any element in the open subgroup K can fix this. So we will call this a smooth. So if any V in these spaces is smooth, that means every vector can be found. We can find an open subgroup to make this fixed. We will call V is smooth. Okay? So that means you just need to find one. So no matter how many, just we can find such kinds of open group. In fact, that's the method to handle the representation here. Same thing. And now we will define the first object here. We will use this notation, G hat. That is the set of the equivalent classes of irreducible smooth representation of G. Yep. Now, in fact, the spaces here maybe it's not finite; it's infinity dimensional. So that means we have to define a suitable condition. We can work on the smooth one. So we will introduce a so-called the admissible meaning here. You see, if pi v is not only smooth n, the dimension will be fixed for any open subgroup of G. The spaces Vk is finite. We call it admissible. So there's something. So we can investigate. There's something like we count the finiteness here. Now I would like to introduce some method to construct the element in G hat here. Just now we have introduced the parabolic induction. We note in the basic theory of the representation theory, we will use some smaller group to construct the representation of the bigger group. So the induction plays the role here. But now the smaller group, we will choose the parabolic one. That means here we choose the M to be a levy in this case, and then the tau here to be an irreducible smooth representation of M here, and then we can get a induced representation. So the space here should be something like that. Here is belong to L1G. This is spaces, and then we choose a regular. Oh, okay. Maybe I choose this. Okay. Now, so based on this notation, we will define the cuspidor. And that this word will come from the heavy triangle. Say, if given a irreducible representations, pi v, which is not induced from the proper Levitt subgroup M. So there's definition of cuspidor here. So that means if there any representation, irreducible representation of G cannot construct in this way, we will call it cuspidor. In fact, we have a fact by Jacquet. Given any element in G hat, we can always find the Levitt M and tau belong to M hat, such that the pi should be isomorphic to the sub-representations of the induced representation of mg tau. Okay. So that means from this we can read some information. For any element in G hat, we can find out such kinds of pair to construct the representation of G. Now, for the purpose of the introduction, the square integrable representation, we have to recall what we call the major coefficient. Major coefficient is kind of the method to determine the type of the representation. So for every pi v, we can construct what we call the contract gradient representation. The V star here is the dual space of V. Okay, so I'll go through the in detail. But in fact, it's one like of we can think for any pi V G. This representation have the unitary central character. So that means the central character means we can, if we add some element from center, we can just only add by the scale character. And we can divide such kinds of function like this. This is a functional. This is what we call the major coefficient. So this depends on from pi v we should construct the contract gradient representation and then to divide some functional in fact to investigate what happened. Now we can divide what is called the square integrable. This kind of notion is all from the heavy triangle. We say pi is the square integrable if all major coefficient are all satisfied. Because G here is the topological spaces, so we have the higher measure, and then we can integrate this. This one is finite. We will call pi is square integrable. So that means we have to classify by the major coefficient in some sense. Yep. From this, we will talk about the London classification. In fact, London classified or representation of the algebraic groups in the following situation. In fact, they prove it. Now we define the temper mean here. If we call a pi v is the temper representation, it means pi is from this kind of object. Chao should be square integrable representation. M is the Levison group. So this is the baby version of the London classification. In fact, we have a lot of detail, but that is the abstract of this classification. So that means, okay, if we would like to get an element G hat, so first of all, we have to find out the square integrable representation, and then we fix the Levi subgroups, and then we can build up all the building block here. But the interesting thing is, in the representation of the periodic groups, we have another decomposition of the G hat here. Everything is based on what we call the Bernstein's variety. This is the following object. S here is a pair. M is the Levi subgroups of G. And sigma here is super cuspidal representation. Yep. And then we have the following decomposition. This stands for the temper dual. That means this is a set of the invariant classes of the temper representation of G. The temper dual we call is called the smooth dual. In fact, this is a disjoint union depends on S. So it's a very nice structure here. So they tell us we just only focus on the given the cuspidal pair. Oh yeah, this is what we call the cuspidal pair. We can build up all the story about the representation of the periodic groups. So now you would like to study what's look like in this object. So what's that? Is there any geometric structure in this kind of stuff? I mean the every part of this. Now we should divide a special quotient space we call the extended quotient. This quotient is come from Alan Coins in 1980. Extended quotient, when you think about the long commutative geometry. Extended quotient. X here is a Hausdorff space, and gamma is a Wien group. And then we can divide the X tilde is as a pair like gamma X subdivide. The gamma X can fix X here. We get the X tilde. And then it's not, this is my first step. We take the quotient one more time on this object once again. I mean, we take the group action of gamma on X tilde, and then we divide this in this way. The double slash. This is what we call the extended quotient. The action here should be given by gamma X to be G gamma X G minus. Yep. In fact, we can have such kinds of decomposition. Yep. In fact, this is also what the disjoint union of the different parts of. This is the gamma is run through the all conjugated classes of gamma here. So maybe this is very abstract. So now I would like to give examples for this extended quotient. Oh, sorry. Okay. Yep. For example, we will choose X to be the unit circle. I mean, the circle. And gamma is a Z over 2Z. It's a finite group. And then we have a group action like this. This is the map. We map this one to this one, and then everything will collapse. And then there's the decomposition will be, this is a unit interval n plus the 2 point here. We can check this. We will get such kind of stuff here. So, you see, everything should be disjoint here. Now I would like to introduce so-called Obey-Baum-Piemann conjecture. This conjecture predicts some reducibility of the representation of the p-adic groups and the geometric structure. Okay, we will have a two group here. T. That's the group of the unramified character, so M, and this is the group of unitary unramified character, so M, where the T is object. In fact, we can classify these two groups by using the Lennon's duality, the Lennon's dual group. Yep. From this, we construct two geometric objects we call ds and es. The ds is the tensor product of the group phi m, tensor sigma. Here, the x, we will call it, x stands for the cuspidal pair. So we have the ingredient here, sigma, and this tensor with the unitary one, we have the two objects. Now, when I talk about the APP conjecture, in fact, this conjecture obey Piemann conjecture. Let's talk about this. the conjecture, this map is bijective. That means we should use the eccentric quotient to study the deal, in fact, based on this conjecture. So, in fact, these two objects is quite complicated. We have no way to compute this. We have to investigate one by one. But the conjecture that such kinds of stuff can be correspond to this kind of funny object here is given by the quotient space. And at the same time, he also implicit some reducibility of the induced representation of the p-adic groups. So the statement here is quite simple, but it's quite intricate inside. Now, so why I would say that? Because the first examples of the conjecture is using the local line correspondence for GLN. So that means in other words, they investigate the case of the G to be GLN. Borsky, the former student of Daniel Quinion, and Pyman, they give the geometric structure for the local line correspondence. For the L parameters. They use the local line correspondence of GLN to prove the ABP for GLN. In fact, we know I would have to say I work on the local line correspondence. This is one of the popular topics in number theory. Line correspondence, local. We have the two objects. This one is the set of the this is the wave group. In fact, we can think about this kind of the Galois group. Then this is continuous L homomorphism to the LG here. LG is the Lannon's dual group up to some conjugated classes, LG0. And then the kinds of stuff to have a correspondence to the following object, the pi G, the irreducible, smooth representations sub G up to conjugations. So there's the plus many conditions satisfy the L function and the fundamentality inside. So that means given any representation of the wave groups, we should have a correspondent to the one class of the irreducible smooth representation of G. Okay? But in fact, in the case of the GLN, it will be more simple, but not very. In 2000 by Ineat and someone, and then they proved the local line correspondence for GLN. They say that such kinds of correspondence is one-one correspondence. So that means any given continuous homomorphism to the LGLN. In fact, the L group, the Lannon's dual group for GLN is G. Okay, yep, that is the GLN over Z, tensor by the Galois. Yep, and that's to be correspondent to the one kind of the just that. Okay, This is irreducible, smooth. This is a 1-1 correspondent, but in fact, you will think we will investigate another group other than the GLN. For example, SLN is different because we have to modulate some conjugate classes. So we have the following situation. Given any L parameters, we will call this kind of stop, we call L parameter. The one error, this is an L parameter, should be corresponding a y like z. The pi I here is the irreducible representations of G. This is not a 1-1 correspondent, but if we consist of in the sum set, it's 1-1. So the element in this set we call the L indistinguishability. That means the pi 1, pi 2 have the same value of L function. But we have some surprising result on this, because using the such kinds of extended quotient, we also can construct the example in this case. So that means, okay, I will need the paper here. Now we choose the G to be SL2 over F. And then we construct something very funny. T is the maximum torus, that means the unit circle. And then we figure out this. Now this representation is parameterized by S here. The U here is the unipotent. And then we can figure out this. Yep. The chi-S here is a unitary unramified character of T. And lambda is the quadratic characters of T. This is the twist. And in fact, we can figure out the pi S should be isomorph. It's equivalent to the pi minus S. And we should record this. The S here is belong to T. So that means this kind of object is parameterized by the circle. Okay? That means any point on the circle stands for one character. And then we send the character into this picture. But now the problem is we have to figure out the reducibility of this representation. So that we're using such kinds of the criterion, we will have the following structure. The pi S, if S equal to 1 or minus 1, this is reducible. Otherwise, it's irreducible. So we have two singular points here. So the pi minus 1 consists of the two different kinds of the irreducible subquotient. One we stand for the pi plus minus 1 and pi minus 1. And the pi 1 we send it to the pi plus 1 and pi minus 1 here. In fact, we go back to this place. We can see that anything happening inside. This circle is stand for the parameter spaces for this representation, and then the gamma here to play the role to justify this condition, the pi s will be equivalent to the pi minus s. So we have the two singular point here is inseparable. That's point 2. So we can see that this stands for minus 1. And then it's 1. So you can see any point except these 2 points on the line is irreducible. But at s equal to minus 1 or 1, split to 2 parts. So these cases explain why the extended quotient can tell me something on the L package. It's quite funny actually. It's quite funny exercise. They also conjecture something on the L package by using the extended quotient. In fact, 3 days ago, they generalized such kind of conjecture on more general cases. So if anyone like to feel interested in this, you can check this, the new preprint on the archive. Yep. Now I would like to state some special case. Now we fix the G to be SL4, and then I would like to show you some picture of the G hat here. For example, if you choose the S is given the cuspidal pair, and now we choose the sigma in this form. The first case, the pi here is the character of QP cross. Then we can decompose this extended quotient in the following way. This is the T2 plus 3 circle plus 4 different points. Yep, in this case, when we fix the S here, we should investigate this part, and then we decompose it in terms of the extended quotient. It's something like that. It's some donuts and the 3 coins and the 4 points here. So how about we change the representation here? For example, if we change a little bit, we choose the first 3 terms, so the same, and then we replace the last term by tau, their difference. And then we keep using the M, is maximum torus. The extended quotient will be decomposed into one donut and 1 coin. Yep. And now, if we fix the sigma to be the chi, the pi tensor chi pi, tensor either pi, and tensor the chi either pi here. Now the chi and eta are ramified character of order 2. In fact, there's 2 kinds of ramified characters of order 2 are common extension of Q2. So that means we choose the 2 edit here. There exists the 2 different ramified characters in this view. In this case, the quotient space is the following. This is the tetrahedron. This is quite funny. So we can see that in this case, we can realize this. Any points on the edge is stand for the characters of T. And then using such kind of character, we can have an induced representation. And then this picture tells us the reducibility of the induced representation with respect to the S can be looked like in this way. So this gives a very concrete geometric size on this dual object. Now there's some result we had before. Yep, we have to say a word. Actually, if we divide a projection from ES, this quotient space, to the ordinary one, the P-image, the any point here, should be the numbers of the induced representation of the T and G tau here. So just count the P-image and then count how many points. In fact, in this case, this point, the vertex, is intersected by the 3 edges, and another one is come from this one. So that means so any point, the point here, we choose to be chi, to be x, and then the chi x, we tensor it with sigma, and then using the parabolic induction, this one should be reducible and consists of the 4 different irreducible representation of G. We have the 4 elements, pi 1, pi 2, pi 3, pi 4, and pi 1 should be sent to this quotient, and other 3 points is coming this way. Okay? So we have the theorem. The ABP conjecture holds for G is the SL2, SL3, SL4, and SLL. L here is a prime number. Yep. So I will have to stop here. Thank you.